I think I'm just going to give a very brief overview of kind of the spatial and spatio-temporal modeling world today. But there's way more material here than we could actually fit into a lecture. I think that there are classes at UW that that get into this thing in more detail. So you can take classes in the stats department, or Jim Thorson teaches a class every couple of years that's Fish 556, I think. And so I think I would encourage folks who are interested in this kind of modeling to dive in and take one of these other courses as well. All right, so we have been talking a lot about multivariate time series data over the course of the class, and that our aims in kind of analyzing this kind of data can have multiple objectives. One of those might be identifying structure, so figuring out R2 time series measuring the same state. But also, if we're interested in doing forecasts or trying to make inference for different time series, we're also interested in making estimates that are also very precise, or as precise as possible given the data that we have. So we've done this using kind of the MARSS type model, where we have a collection of time series, and then we map them onto latent states. And then we have models like the DFA approach, which is not mapping time series directly onto states, but is estimating what those weights are via these loadings. Okay, so this is just, graphically, if we have two time series modeling the same state, if we also include some information about the correlation between these time series, we're going to get just better predictions about the overall trajectory that this population is following, as well as more precise estimates and inference about what they're doing individually. So I think using this kind of shared data or information is going to give us better estimates. Okay, so I think that the last couple of weeks I was talking a little bit about some of these Gaussian process models, and I was demonstrating that if we have these very large covariance matrices, we can run into all kinds of estimation problems, because especially with kind of the short time series data that we are collecting in fisheries and ecology, we're often not able to estimate all of those parameters. And so in MARSS, we have a number of ways that we can kind of constrain those matrices, so we can make them have equal elements, or make the off diagonal different than the diagonal. And then, of course, DFA runs into the exact same issues that MARSS does. So I think there's a number of folks who are working on final projects that involve collections of 10 or 15 time series, and you'll find those models take a very long time to run, especially if you have these unconstrained observation error matrices, just because of this dimensionality problem, which you can't really get around in that MARSS type framework. So we need to think about other options. And I think a number of folks, actually, I probably guess that more than half the people who are working on these final projects have some kind of spatial structure in your data. So either your sites are kind of grouped together, or your sites might be on a river network. And so I think you're already thinking about these kinds of questions, I think. In terms of kind of biological mechanisms, obviously, I think there's a couple local examples that I can think about related to some of the data that we've provided in the MARSS package. The first is thinking about kind of the correlation structure among populations of salmon that might be returning to Puget Sound, for example. There's been a lot of work done on this at the Northwest Fisheries Science Center, and there's essentially 21 different populations that are recognized as these distinct populations. But we can think about including spatial information in terms of modeling the similarity in their dynamics. But there's also other factors that contribute to that correlation, or I guess, in addition to the spatial information, there's other factors that contribute to their synchrony. And so one of those might be the genetic similarity of the populations, which is largely has been driven historically by these large hatchery programs, for example. Another example is that we think about kind of the shared dynamics of some of the harbor seal trajectories that we've been working with in Puget Sound. Some of them are affected by the presence of killer whales, for example, that are predators, while others are kind of immune to that. So I think we're interested in potentially including that external information in addition to the spatial information. Okay, so I think one of the benefits of thinking about explicitly dealing with the spatial problem instead of having a giant covariance matrix that we might have in MARSS or other tools like Eli was talking about. The alternative here is to just explicitly deal with space and develop some models that will incorporate that spatial correlation. In terms of the estimation side of things, doing this will greatly reduce the number of parameters that we have to estimate, going from a giant matrix of 100 parameters to less than 5 usually. Okay, so when we talk about spatial data, I think it's important to clarify exactly what we're talking about here. Most of the data that I'm talking about in the context of this lecture and for this class is going to be what we'll call point reference data or geostatistical data. And so geostatistical data is the kind of data that we might collect as part of like a fisheries survey, where we go out to given locations, and at each of those locations we measure, say, the density or catch per unit effort of a variety of different species of fish. So it's spatially random. It is, and then we could visit the same stations repeatedly, or we could not. It doesn't really matter. But that kind of data is geostatistical data, where we have a series of observations and a series of coordinates that are accompanying those observed values. The second kind of data are what are referred to as point pattern data. And so I'm just going to distinguish the geostatistical data from the point pattern data in saying that the point pattern data don't necessarily have an observation that's associated with them. So these are just locations. So you can think about this could be like the locations of trees in a forest, and you're interested in whether there's a random distribution, or whether there's some clustering process that determines which species are found where. And so with that kind of data, we don't have a measurement associated with each point. We just have a series of points. So those are kind of the two kinds of data associated with points. The third type of data in spatial statistics is known as aerial data, and these are described as anytime you have data or locations that might be not referenced by latitude longitude but occurring in blocks. And so these could be any kind of data according to like counties or precincts, that sort of thing. And so if we look at the city of Seattle and we wanted to measure we want to develop a model of some attribute of health outcomes, for example, and we wanted to use kind of the Seattle Council boundaries, this type of data would be aerial. And we'll work with a little bit of aerial data, but mostly work with the kind of the point process data. Okay, so in thinking about different ways we can analyze the data, I'm going to kind of start with some of the most computationally friendly approaches, and we'll kind of get a little bit more complicated from that. The first set of families of these types of models are what are called CAR or SAR models. And so CAR stands for conditionally autoregressive models. And the SAR models stand for simultaneous autoregressive models. There's a typo there, sorry. But the goal of both of these is essentially to develop a model that will make predictions for a set of points given the neighboring data. And we'll kind of go through some examples for each of these. So the CAR models have been around for quite a while. And they are, they're very similar to the models that Eli was just talking about in thinking about, models with correlated errors. And so if we look at kind of the basic equation for the CAR framework, we have some response Y, we have our regression coefficients, betas, the design matrix X, which are just our covariates. And then we have this vector phi and some residual error. And so if phi wasn't here, we would just have a simple linear regression. And the presence of phi is just the spatial component that we're going to be including, and that's the piece that's really unique to these CAR models. So the phi in these models represents a kind of a static Markov random field or static spatial field. And we'll walk through an example and show kind of what that means. And so, you know, we're going to be talking about in the context of these CAR and SAR models, we'll talk about creating a neighbor matrix or an adjacency matrix that we'll call W. And so this is based on which values are going to be neighbors with each other. I'm thinking about this in the context of you know, the aerial data, like I was talking about with the Seattle city council maps, where we're going to be looking at which districts might be neighbors with each other, rather than the point process or geostatistical data, which is referenced by latitude longitude. So we're going to create a matrix, this W, that's based on our neighbors. And so if two separate spatial blocks are neighbors, that matrix will get a 1. If those values are not neighbors, it'll get a 0. And there's a bunch of different constraints for estimability that we have to often include, like W has to be row normalized. And then finally, you know, the diagonal elements of W are going to be 0. And so any, you know, normally we would think that if a cell was, if we're interested in mapping neighbors, any cell would be a neighbor with itself. But as I'll show in a second, for computational reasons, basically the diagonal of that W matrix will be 0. Okay, so just thinking about what this looks like, maybe for a hypothetical stream network, we have 5 sites here on a stream. And if we wanted to develop kind of the adjacency matrix, or W, for what this would represent, this is basically as simple as it gets. So site 1 and 2 are neighbors. 2 is also a neighbor with 3, but 2 isn't a neighbor with 4 or 5. And so that's fairly straightforward. In some cases, people have also used other weights other than 1, and so these are values that you would set a priori and not estimate. But you could specify alternative values here if there was some justification or you wanted to try that. But for the most part, you know, these models are very commonly used, and most people just use the value of 1. Okay, so the difference between the spatial regression, or the kinds of regression that Eli was talking about, and the spatial regression, is that we assume that the spatial values are going to be essentially random effects. And so this vector phi is a vector of random effects that corresponds to 1 value in each site. And earlier I'd said that these values are static, and what I mean by that is that we're going to estimate a single spatial field that's shared across all time slices, rather than estimating separate values of phi maybe for every point in time. And so we're estimating basically a vector of random effects that's dimensioned in terms of our numbers of sites. So this is going to be random effects. It has mean 0 because the intercept and all the covariates in the model are going to be sucking up the rest of the variation, and that will be the mean. And then they'll have this messy thing here on the right will be kind of what the covariance matrix is. And so this form is kind of the CAR formulation of the covariance matrix. It's implemented in a bunch of R packages, and generally we don't have to do anything with this. All these functions will kind of deal with the messiness of this ourselves, the messiness of this internally. The only thing we really have to specify is what that W is, which is our matrix of zeros and ones describing which cells are going to be neighbors with each other. Okay, so with a CAR model, if we don't think about it in matrix form, I think it makes a little bit more sense in that, we think about the random effects, or the reason why it's called a conditional autoregressive model is that we think about the random effect for cell I is going to be conditional essentially on all other values so the rest of the random effects, or the rest of the spatial field, and it's just driven by this formula where we're going to take our W matrix, and we're going to take the all elements of that matrix corresponding to this row, and multiply it by the remaining values. So it's just going to be a weighted average of all of the other values with some estimated variance. And so the W matrix is just going to be giving us assigning the weights to determine what, how these values affect the random effect in question. So you could envision doing this for the first value of phi, and then doing some iterative procedure where you were just looping through and sequentially updating each of the different phi values. Okay. So to just take as a tangent, I talked about the CAR model and the SAR model as both being used. There's slightly different versions of trying to do very similar things. In both cases, we are just going to be estimating a single parameter. In this case, we're estimating a row parameter, and we're passing in both cases this adjacency matrix, the W. Both of these formulations on the top and the bottom are essentially the distribution of that vector phi for the random effects. You can see on the right, the CAR, this CAR piece is a little bit simpler, but everything here on the describing the variance covariance matrix is also in the variance covariance matrix of the SAR model. And so the only thing the SAR model is including is this additional weighting. Otherwise, they're exactly the same. And in both cases, we're also, in addition to estimating this row parameter, we're estimating kind of the overall variances, which are described by D. I'll show some examples. So in the simplest form, I think we're going to be estimating a row, which describes the weights or the weighting of the W matrix, and then a single sigma if all sites are sharing the same variance. So in the simplest case, D will just be a diagonal matrix of values sigma. Okay, so to kind of just to show what this actually means, we have this quantity I, which is an identity matrix minus row times W, and so if our W matrix just looks like this, and we assign a value of row, you say if row was 0.3, then all of a sudden, the quantity I minus row times W, we have a diagonal on a diagonal of 1, which is good because that is just essentially going to be the correlation matrix, and then the values on the off diagonal here are minus 0.3, and so values of row that are positive are going to be corresponding to negatively correlated neighboring cells. Okay, so again, the last piece here for the CAR model is taking this matrix of D, which is going to be basically describing the magnitude of the variances. And so if we assume that D is just a diagonal with the same variance, when we multiply that by this quantity, which is the correlation matrix, then we get out this variance covariance matrix here. So that's what the calculation would look like, and that's kind of what the output would be. So then we would assume that our random effects were distributed multivariate normal with this variance covariance matrix. Okay. So the kind of the common threads of the SAR and the CAR model are that that matrix W can be modified to include, as I said, other values other than just 0 or 1. We can include other things other than distance, and I think one of the simple things is that we can include that spatial dependency, or essentially the weight of that W matrix. We can describe it just by estimating the single row parameter. That's what's used in the majority of all CAR and SAR applications. There's a few extensions that use slightly more complicated versions, but for the most part, we're turning this complicated estimation problem into just estimating row, and then as many variances as we want to estimate ranging from 1 to the number of sites. So these models also, as I was saying, are estimating static random effects, and so they're estimating a spatial field that's common across all of the different time dimensions that might be in our data. And so I think we could potentially extend these models to include that time dimension if we wanted to draw, say, phi vectors that were unique to each time slice. So we could have phi drawn from I equals 1 to t, where t was the number of years that we might have for our spatio-temporal data. So this could be a lot more complicated. Most CAR applications and most CAR packages that you can work with are just going to have the options for just using the single spatial field. Okay, so I think in feedback for a number of folks for the final projects, I was probably at some point recommending the BRMS package, which is really flexible and does a lot of great kind of hierarchical and GAM modeling in a Bayesian framework using STAN. And so BRMS is also kind of in the family of packages like what Eli was talking about that include the option to include some of these ARMA type errors or correlated errors. BRMS also includes the option of including these SAR and CAR models, and so you can look at the examples just in the vignettes or the manual, and I'll go through some examples with BRMS in a second. So maybe the downside of using these types of approaches, and one of the reasons why it's probably not one of the most go-to tools or ways I'd think about this problem, is that a lot of folks have thought about how the distances between the neighbors or the essentially they've thought about what the W matrix, or this matrix of weights, what that is implicitly assuming about the relationship between distance and correlation. And so you would envision in most kind of spatial models, or the Gaussian process models that I've talked about so far, we kind of assume that correlation is going to be declining as a function of distance between locations. And so that's essentially what this simulation paper did, where we have a few measures of distance on the x-axis, and then on the left and right panels, we have the implied SAR correlations and the implied CAR correlations. And the really troubling thing here in this result is that these approaches don't assume a one-to-one mapping of distance and correlation, and so that just means that at a given value, or at a given value of rho, we could get potentially a wide range of correlations, and not all of the correlations would be the same. So we could have, I'm just thinking about like the river network kind of image that I was showing earlier, maybe two sites that are close, like site 2 and 3, might be the same distance in space as sites 4 and 5, but one of those pairs would be much more correlated implicitly, just based on how that matrix was formulated. And so I think because of these just weird relationships, that's one of the reasons why I kind of have steered clear of these approaches, but they are still pretty commonly used, especially for the aerial type data. So the alternative to CAR and SAR models are going to be kind of akin to the Gaussian process type models that I've talked about so far, where we take our process variance covariance matrix, which I'm calling Q here, and we're going to model that as a series as a function of distances between locations. Those distances could be indexed by time, and we've talked about that. They could also be indexed by space, and so that's kind of the step here, is that we'll be using Euclidean distances between points in 2 dimensions to determine how quickly that correlation is decaying as a function of distance. And so there's a lot of different types of approaches for doing this. I think One of the commonly used functions is this squared exponential covariance function. And so I've talked about this a few weeks ago. The covariance function just describes the covariance between two locations, x1 and x2. D here is going to be data. This is going to be the squared distance between those locations. And we're only estimating two parameters here. So sigma controls the variance, or how basically the the intercept on the y-axis here, and then theta is going to determine how quickly that covariance is decaying as a function of distance. So when theta is large, sites that are far apart are going to be more correlated, but when theta is very small, it means the correlation is going to drop off really sharply between locations. And we can think about this with simulating time series when again when theta is large. The dynamics will be very similar even for sites that are far apart, versus when theta is 1 or theta is even smaller, we're going to get values where every time series is essentially spatially uncorrelated with all others and will be basically behaving as a random walk. Okay, so that, I think that there's a large variety of different types of covariance functions to choose from. I think I've talked about some of these with relation to the Gaussian process stuff, but some of the commonly used ones are the Gaussian covariance kernel, the exponential, and the Matern are probably the three most commonly used. Just thinking about what these might look like for a given data set, these all give us very similar spatial fields. And so if you just look at this with your eye, they look basically identical. And the point of this is just to highlight that these all three models are very flexible and can give you very similar smooth surfaces. You're going to see differences between them as the models become more complex, but I think for most purposes, I think that these are going to be somewhat similar. And to illustrate sort of maybe what you could see as a difference, if we were to take kind of the values on the previous screen, so if we were to simulate the spatial field using 3 different covariance matrices with the same decay parameters and the same covariance, and then we were to look across all 3, and then for a given point subtract the mean, we can see where some of the functions are giving higher values or where some are given lower. And so, for example, when the exponential here is blue, it means that essentially the covariance of these points, or this collection of points, is going to be higher, or those predicted values are higher than the others. And so, in general, people refer to the exponential and Gaussian covariance kernels as being a little bit more smooth than the Matern, for example. I don't know that you can really see that with your eye, but that's I think that there's some very subtle differences between the 3 different approaches. Okay, so thinking about some of the considerations for the time series models, I think one of the biggest questions in kind of starting to develop the models are after deciding that you want to include spatial dependency or include the spatial correlation between locations, then we have to think about how to model it. And so I think we could take the kind of the CAR or SAR approach, where we are going to model essentially static spatial variation, and so estimate a single spatial field that's shared across all time steps. Option 2 is going to be maybe we could try to estimate separate spatial surfaces for each time slice in our data. And so in that case, we could think about those as being totally independent. We could think about them, or we could think about them as being more complicated. And so if they're independent, it just means that that spatio-temporal variation is going to represent some process that we don't have covariates to explain in our data, and that's going to essentially represent, it's not residual error, but it's going to be just the random year-to-year variation in that spatial field. Thinking about how that spatial field might change through time, we might have a situation where that was independent, but we could also have a situation where, essentially the spatial process itself could be modeled as a random walk. And so in that sense, if we think about just taking the spatial field and modeling it as a series of random effects, you can think about modeling that vector of random effects as being centered on the vector, the time step before, and so forth. And so you can think about that spatio-temporal field as being this autoregressive process. It could be a random walk, and so instead of having that autoregressive phi to help it be stationary, maybe it could just have a random walk and kind of wander off into space. I think the interpretation in those kinds of autoregressive or random walk models would be that that hot spots one year or cool spots would typically be hot spots the next, and so we kind of have that that autoregressive process, right? And they can be independent. Okay, so there's a number of different model-based approaches for dealing with this. I think that we'll talk through some of these. These are in no particular order. And what I'll try to do today is kind of break these into examples that are based on the spatial regression type approaches, and then examples that are based on models that assume an underlying process. And so more of the state space models akin to what Eli was talking about. So yeah, there's generalized least squares approaches. Eli talked about GLS. There's Bayesian methods using a number of packages. There's approaches that are based on INLA, and I think that these are the kind of the extensions of these are wrapped up in TMB, especially through VAST and SDM TMB, and we'll talk about those on Thursday. And spatial GAMs are kind of the other approach that we'll talk about today. Okay. So using GLS, GLS is it's a function that fits models using least squares. Exact same formula interface as using LM or GLM or the kinds of functions that you're familiar with already. But GLS includes a number of different flexible correlations on top of the basic linear model that allow us to fit kind of a spatial process. Unlike some of the time series models that we've used, I think like some of the ARIMA based models, GLS is flexible in that it lets us fit values with NAs. So that's one of the positives. Okay, so the example data set that I'm going to be presenting or talking through a little bit will be data set from Washington State. It's collected, I think by the state and a number of federal agencies. It's collected the data on snowfall that's collected at a series of these what are called SNOWTEL sites throughout the state. This kind of data I think is nice, given that so much of my work and applications to these kinds of spatial models are on fish populations, for example. Snow data is really nice because it doesn't move around, and so I think we'll be modeling this across 70 stations in the state. And this will just be, while they do have measurements that are collected monthly, our analysis here, we really focused on just looking at data for the month of February, which is corresponding to one of the more snowy months. So we have 70 some odd stations, and we'll be using this time series of data that's about 30 years long, from 1981 to 2013. It's very data rich, and there's very few missing values. So that's a positive. Okay, so if we wanted to fit this kind of model using this GLS, like Eli talked about a GLS example. This is essentially what we would do, where if we wanted to model essentially a linear model where we were treating the February snowfall as the response, and we wanted to treat elevation as being the only covariate to determine snowfall, we could think that maybe higher elevation would lead to more snowfall. In addition to the elevation effect, we're going to be including a spatial process. And so the spatial process just might incorporate things like differences in snowfall between the east and west side of the Cascades, or differences with respect to latitude, or just where that data is being collected. So it's representing the part of the spatial, it's representing the spatial process that describes kind of snowfall patterns in the state across years that is not driven by elevation. Okay, so to set this up, we would use the typical formula with elevation as the predictor, and then we specify our correlation function in this form. And so it's very, very simple. This is assuming that there's a single spatial field that's shared across each of our time slices. And then we're going to model it as a function of latitude and longitude. So this is the simple exponential covariance function. If we wanted to contrast this with a function that was modeling, say, the Gaussian covariance function, we could just switch the covariance function here and do the exact same thing. There's a number of different ways to compare, which of these models fits better. You could use a model of predictive skill or fit. In this case, we could just use AIC to look at which of these is leading to lower AIC values. And it seems to be slightly better support for the exponential over the Gaussian. Okay, we'll look into that a little bit more. So these are very similar. There's also some useful diagnostics in that GLS function. And so I think if you're interested in doing this, one of the common tools that people use for diagnostics are using kind of producing these variograms, which are another way of looking at how distance determines the correlation between locations. And so the variogram function is something that would take one of our fitted GLS objects, and it's going to make a kind of a couple of plots. So we can just compare what these might look like between the two different exponential and Gaussian models. So here's what the plot that we typically might look at. This is called the semi-variogram. It's always a little bit hard to wrap my head around, because normally we think about how covariance or correlation decays as a function of spatial distance, but here what we have is essentially the distance is on the x-axis, that's increasing, and the semi-variogram is another metric of the variance or covariance between sites. And what we want to kind of the language here is, there's going to be some distance on the x-axis where the covariance between locations is going to basically be flat or level off. And so we're gonna describe wherever that distance occurs. Let's say it happens at 1.2. We're to describe 1.2 kilometers as being the range. And so high values of this represent, so it's kind of a mirror image of what I was describing with covariance declining as a function of distance. Here we're saying that the semi-variance is increasing as a function of distance, and sites with high values are going to be uncorrelated. And so so essentially this is useful for looking at kind of where's the point by which basically at what distance does covariance really drop off and our sites no longer correlated. So the blue line here represents essentially the assumptions about the exponential fit through those data. We can see it sort of works okay, but it's definitely not asymptoting very quickly. But I think looking at the exponential, we can also kind of contrast that with the Gaussian. And maybe one of the reasons why the exponential, even though the exponential doesn't do great, maybe the exponential has slightly lower AIC because it seems to do overall a little bit better than the Gaussian, which tends to miss a lot of this. It should have asymptoted a lot earlier. So so these are the kind of diagnostics that we can look at with GLS and other packages, but that's just kind of the intro. Okay, so with GLS, I talked about the exponential and Gaussian kind of spatial structures. These are also widely available in a number of other packages out there. So we can include these in essentially any of the linear mixed effects models that you might be familiar with, or in MGCV, we can include them in GAMs too. So, so very flexible. And once you kind of get this structure and understand what the arguments are, you'll see it's I think a lot of people developing packages are developing them to be similar so that the arguments are basically the same. Okay, so option 2 is going to be talking about modeling GAMs, and I think we haven't talked about GAMs a lot in this class. Getting back to what Eli was saying, I think that GAMs are very flexible at modeling some of these spatial processes, and just like with time series, they're very flexible. But they're not modeling an underlying state process in the sense that it's not an autoregressive process, for example, describing the relationship between the latent state at time t and the latent state at time t+1. So another kind of distinction between GAMs and some of the other models, like the CAR or SAR model that we talked about, was in the CAR or SAR framework, I was describing the spatial random effects were being they were being generated from a distribution that was multivariate normal with some variance covariance matrix, and we were really manipulating the variance covariance matrix via that adjacency matrix, that W. But with a GAM, we're going to be thinking about it as instead of modeling those random effects, we're going to be modeling GAMs. And I'm sorry, I'm confused because these are not exactly the slides that I uploaded. Eli, I wonder if there's something that got crossed with our lectures or something. Anyway, I'll update these, but I've seen a few issues. Okay, so getting back to kind of our snow data and thinking about a simple GAM type model. With a simple GAM, we're going to be modeling, again, February snowfall is a function of latitude and longitude. We are going to be setting this up so that we have our GAM call down below. We're going to be modeling the water year itself also is a smooth process, just to incorporate the variability from year to year. And then we're going to be including the spatial process, or the spatial smooth, as being this two-dimensional function of latitude and longitude. Okay, so that's how we would fit the model. It's fairly simple, and a lot of people have probably already fit these two-dimensional smooths using GAM and MGCV before, so that's great. We can also get the residuals out of GAMs the same way you would with a linear model, just with the resid function. So that should be familiar. Okay, so for diagnostics, one of the things we might want to look at is, is this pattern going to be essentially stationary in the residuals? So this would be an indication that our model is doing a good job describing the overall pattern. I think if, for example, there was maybe spatial autocorrelation in the spatial field, we might see the residuals might be kind of also showing an autoregressive process, in that there might be years where things were above or below average, for example. And when we look at kind of diagnostics for doing that, there's certainly clusters of years where the model fit is not great, but overall it seems like everything is stationary. Okay, so the second thing we could do is kind of take the residuals and plot what they look like over space. And so I think I've said this in a number of kind of feedback to student projects, but if we fit these kinds of spatial models and include complicated structure, one of the things that we want to see is essentially, we don't want to see any trend over time, but we also want to see no trend over space. And so we want to see we don't want to see any presence of spatial autocorrelation in the residuals. But when we look at these, it certainly seems like not only are there years where there's big patches, like 2005, the residuals are very negative, or 97, the residuals are very positive together. But there also seems to be within a year quite a bit of clumping of similar colored points that are clustering together. So without running kind of formal spatial correlation statistics like we would with GLS, for example, it certainly seems by eye that there's some correlation that the model is not doing a very good job describing. It's probably not a surprise because the model is also very simple, but ideally what you would do would be to take output from this kind of model and then use any of the spatial stats programs to calculate some measures of dependency. Okay, so what do these interactions mean, or what do the fact that our model didn't do a very good job tell us? Well, one of the things might be that I'm just going back to my plot. One of the things might be that I fed a model with just a single spatial field that was shared across years, and it included a time effect, which just let the overall intercept of that field vary through time. And so maybe in practice, it'd be better to fit a model where we allowed each year to have its own spatial pattern that was different from all other years. And so the way to do that with a GAM is, we have our two-dimensional smooth, and then we're going to be including this by term, which takes a factor. And so here we're going to be smoothing it by year, and this will let each year have its own spatial surface. Okay, this has the exact same smooth for the overall year effect, and so this just controls the intercept. Again, it will just separate out kind of high and low snowfall years, and model that as a smooth process through time. Okay, so that would be one way to think about it. Another would be, instead of having that spatial effect be in the last model, we had different spatial effects that were being estimated for each year of our data. In another case, we might think that that maybe instead of having that spatial, basically the interaction between space and time as being discrete, we could model that as being continuous. And so in this case, a way to model the space-time as being continuous would be to have essentially a single spatial field as a function of latitude, longitude. Again, our same smooth over the year effects to control kind of the intercept, and then we're going to be using this interaction, which you can get with this tensor smooth in GAMs, and that will give us the interaction between longitude, latitude, and year as a numeric interaction that's continuous rather than discrete as before. So I'm not going to get into this. I know it's fairly into the weeds and jargony, but this is the kind of complexity that we could adopt if we wanted to try to fit those kinds of models. Okay. As I've said, I think there's a ton of other really good useful materials that are out there for fitting these kinds of models with MGCV. We can include all kinds of random effects, do it in a Bayesian setting, etc. And a bunch of these guys have developed a workshop or a series of workshops, including at the ESA meetings. And so I would definitely check those out if you're interested in fitting these types of models to your data. Okay, so I think one of the limitations of, despite their flexibility, the limitations is that unlike some of the CAR and SAR models that we were fitting, or even the models with GLS, a potential downside with the GAMs are that we're not explicitly including a covariance function or kernel, and so that's a difference. It's also hard to add constraints. And so in terms of thinking about if we wanted to model a autoregressive process that was where the spatial field was dependent upon the estimated spatial field the year before, and letting that be a random walk through time, we can't really do that with a GAM. And so that kind of sets us up for using some more custom approaches. I think these are, yeah, I think that these are slightly different than the slides. I'm gonna probably
hey,
just,
Eric.
yeah.
So go back to the website, and I fixed, I think, the problem. It's uploaded lecture 18, but it should be the exact same name, but lecture 17. So if you just go there and re-click on it, hopefully I fixed it. Yeah, the second one.
This one?
Yeah, number 2. See if that works.
Let's see here.
Now showing 17. Okay, hopefully that works.
Okay. I'm gonna stop. I'm gonna leave the GAMs there. All right, these are right. Yeah, right. Yeah, so I did actually have another example using VRMS that folks can walk through on their own. But I just wanted to show like how flexible this is for doing this. So you know, there's this COVID tracking project that has a lot of time series for different U.S. states, and I think it's a pretty huge data set. I don't understand very much of it, and so I think there's a lot of different nuances and things, and so I'm not really trying to develop an epidemiological model here, of course, but I'm just trying to use it as an example of how we might set up an example with a kind of real world aerial data, because the map of the U.S. is really complicated, and we have to describe this adjacency matrix to fit the model. So this is the data from the COVID tracking project. I've included it in the folder, and I'll make sure it's linked on the web page for the class. But basically, we have, there's a number of ways to plot this, but this is just essentially the number of positive cases by state as a function of time. And so I just filtered this by essentially April 1st of 2020 to the end of last year. Okay, so I think one of the things that we could think about is, just there's some simple summaries that we could try to model here. For example, one might be the difference in the percent of positive cases and how that's changed through time. And so I think in this case, this block of code it's just gibberish without having the data, but essentially we're just grabbing the fraction of positive cases on December 31st and taking the log difference of that and the percentage of positive cases on April 1st for each state. And so that's going to be the response. We're going to fit a CAR model, and we'll just have a single value because the CAR model is going to be estimating a single spatial process and not considering essentially the time dependency. So so to do this in BRM or BRMS, it's super simple. Essentially we need to create this adjacency matrix W, and I've hidden the code to do that, but if you want to go do it yourself, it's on the lecture notes. But essentially we just have to create this giant matrix W that here is going to be dimensioned 48 by 48 because I didn't deal with Alaska and Hawaii. But we pass that in as our covariance matrix and specify our error structures being this CAR process. We don't include any covariates, of course, but the model is fast and fits in a minute or two. So I think you can do this on your own, but that's essentially how BRMS does it. It's very, very flexible and fast, and so I'd recommend using that as a tool if you're interested in kind of adopting these types of models. I think with that, I'm going to just we'll just kind of leave it there for for GAMs, and then pick up with other models maybe here on Thursday.